to be able to share free energy equilibrium with you guys. Now, I'm going to fly through this because there are other videos that have all the information and might be a little bit better at sharing this information with you. My video here is going to target how do you tackle these type of questions. So let's rock and roll through this. Free energy at equilibrium. Free energy is Gibbs. That's the delta G. Okay, and we've been working with this already. We've done a little bit of work during 9.1, 9.2, getting to know entropy, getting to know what is free energy. Now, if the free energy is 0, so let's say delta G is negative. If it's negative, then that means that, this reaction is going to happen. It's going to happen in the forward direction. But if, let's see here, what do we got? We got a pen? Yeah. So if delta G is negative, then that means that this is going to happen in the forward direction. We call that thermodynamically favored. If delta G is positive, then it's not thermodynamically favored, and it's going to likely happen in the reverse direction. Okay, so now what if delta G is actually equal? Let's say that delta G is equal to 0. Delta G is equal to 0. Okay, that's equilibrium, and I purposely drew this right over top of this. If delta G is 0, then it's not favored in either direction. It's an equilibrium. So it's basically you have both arrows. Okay, so let's go back here. Let's turn this pen off and let's keep going. So you can set delta G equal to 0 to find other variables at equilibrium. And they ask you to do this on one of the problems for sure on the assignment. I believe it'll also come up on one of the quizzes. Okay, so calculating, and you can use K using free energy. You can, now wait, so that means if we're at equilibrium, now we've got K involved. And we remember, okay, big K means it's going to go forward, little k means it's going to go backwards. We've already learned that. But in this case, we're going to use the natural logarithm of K times the temperature times the R value. Now, which R value do I use? Because there's two of them on your equation sheet, on your formula sheet. You're going to use 8.314 joules. Notice that we've got joules. You're not going to use the other one, which is for gases. You're going to use the R value that's for energy. Okay, and if you're like, well, how do I know which R value? Look for the joules. Because anytime you're calculating with delta G, you're talking about energy, you're talking about joules, etc. Now, they don't give you this derivation on the equation sheet, but it might be nice, at least for one of the problems, to be able to work on it to find K using this. If you are using, what's the word I'm looking for? Let's say I need to solve for K. Let me see if I can switch back to that pen really quick and see if I can show you guys very quickly. So if I'm going to solve for K, I'm going to divide both sides by R and T, okay, negative RT. And then I come over here and I divide it by RT. This is a little painful, team. I appreciate your patience. Now these cancel, and I'm left with the ln, okay, of K. Now, how do I get rid of the ln? I basically will say, okay, e to the power of all of this. E to the power of all of this, and e to the power of the ln of K. Then ln and e cancel, and I'm left with K is equal to e to the power of delta G over, and that's all in the exponent, and you can see that written right there. So that's where that came from. This was like, some of my students were like, oh, now that I can see that, that makes more sense. So what if I need to be able to calculate the reverse K, the K for a reverse reaction? So all you have to do is you go K divided by 1. That's it. K divided by 1 gives you your reverse reaction K value. Okay, so we got to remember delta G and K for meaning for the reaction directions. Okay, we already talked about this. Delta G is negative, then it's thermodynamically favored. It's going to go forward. If it's not thermodynamically favored, it's going to go backwards. And then if it's that's zero, then it's at equilibrium. Okay, so that means that the K value, if K is positive, then the ln of K is positive. If K is equal to 1, then the ln of K is 0. If K is really, really small, okay, greater than 1. So if K is greater than 1, so it's a big K, ln of K is positive. Little k, ln of K is negative. So this is if it's a forward reaction, we have the ln of K is positive. Reverse reaction, or the reactants are favored, then we have the ln of K is negative. Okay, one thing that we need to be willing to pretend is sometimes you need to be willing to say, okay, let's pretend that one of these variables is positive or negative. How would that affect the final result? So for instance, what would change what would the change in H have to be compared to the temperature times entropy for the reaction to be thermodynamically favored? So, for instance, let's say if we're trying to find thermodynamically favored, you're like, okay, this has to end up negative. So then you're like, okay, so ideally, okay, we come here, so I've got a negative T times, so if my entropy, okay, where delta S was negative. So I've got a negative T times a negative S, that's positive. Okay, so that means that my delta H would have to be negative in order for me to be able to get this. And it would have to be significantly negative to be able to get rid of that and then go back and make this overall negative. And you kind of have to play around just like I did to be like, okay, what would the change in the change in H would have to be negative most of the time for it to be thermodynamically favored. Now it could be positive, but you'd have to figure out what would these other variables need to do. They'd have to be significant in order for it to be able to end up with a thermodynamically favored negative delta G. So thank you, team. Appreciate your time on this. I wish you success. Please tackle each one of the questions. Turn it in. Let's rock and roll.